All right, how's it going, guys? We got another Navier Stokes problem. This one's for a layer of viscous fluid of constant thickness, which means that H is going to stay the same along the fluid flow. It flows steadily down an infinite inclined plane. There's no velocity in the y direction, perpendicular to the plate. We need to determine the relationship between the thickness of the layer and the discharge per unit width. In other words, just the flow rate per unit width. Okay, using a Navier Stokes. So air resistance is negligible, meaning shear stress at the free surface is 0. Now that's important because that's going to help us determine the boundary conditions for this problem. So let's go ahead and get started. All right, guys, so they want us to find an expression for the pressure gradient in the direction of the flow in terms of the mean velocity. So we're going to use the Navier Stokes equations to develop that expression. And, you start off at step number 1 here, and that's just the figure here. You start off with the equation, right? In this case, I'm using the y component because this is the xyz of the problem, and the flow is going upwards, right? So I will be using the Cartesian system, right? It's just xyz, no polar coordinates, none of that. And it's in the y direction, so the y component, and that's just this right here. Okay, so this is the one that you see in the book, but what I like to do is I just like to divide by density to everything. So all this stays how it is, right? Up to here. You have a -1 over density, right? Because this is negative as it is. You have just gy, right? Because that density went away. You divide it by density both sides. So, and then mu over density, that's just nu, okay? So I just replace it there, and then that's it, okay? No big deal. So we start off with the equation, and it looks scary, but you just start simplifying from here. It's pretty straightforward. You'll see that this crazy equation kind of just reduces to very workable terms. So we go ahead and do that, right? Let's start doing the assumptions from the problem. So you're dealing with steady state. Anything in the undergrad course is going to be steady state, just FYI. Very rarely do they give you guys unsteady state. Maybe crazier schools like UCLA does, right? Who knows? But I know my Cal State just gave me a pure steady state problems for the undergrad, so I'm assuming that's why you guys are here too. So steady state, right? The t term, anything with a t, is 0 because it doesn't change with respect to time. It's steady. So that's 0. So that term went away, okay? The flow is only in the y direction only. It goes up in this case, right? So since we're going up, gravity is bringing it down, just something to keep in mind. So that means there's something pushing, fighting against gravity, kind of pushing it up like a pump or something. But I mean, that doesn't matter. That's just kind of like to get you guys to think a little bit. That's why the flow is going upwards in this case. So the flow is in y only, okay? So u, which is the x component, velocity in the x, velocity in the z is 0, okay? So just like that, that term goes away, u, and then w goes away, boom. The body force, okay, that's just what I just said right now, that there's only gravity acting on the system. There's something pushing it up, but in terms of body forces, there's only gravity, okay? And because it's in the y component, you have a -g. All right, sometimes it's at an angle, so you got to get like sine theta, cosine thetas. But in this case, it's going straight up. So it's just -g, okay? And you got to remember the negative. Right here, it's positive, but once you put it in, you're going to have a -g. And then infinite plates, what that means is going into the paper, the flow doesn't change. So look, I kind of drew this here to help you guys kind of visualize it. Here, it's the same. Go into the paper, it's the same. It's the same. It's equal going into the paper, okay? So there's no change. And that's what that means. The change in the y velocity, right, and the upwards velocity with respect to z going into the paper is 0. There's no change. So take the second derivative of that, and that's just also 0. So this term went away, and vz, this one went away. But the w had already gone away, so it didn't really help us. But this one went away, so that's good, right? So now we go to the conservation of mass. To eliminate even more terms, right? We know mass is conserved in the system. So when you start applying it for Cartesian coordinates, this is the mass conservation equation, right? The change in u with respect to x plus v with respect to y plus w with respect to z, all that's equal to 0. but we know that u and w are 0. So anything in the x and z, there is no velocity profile. So that's just 0. So take the derivative with respect to y, right, for delta v, delta y. I'm sorry, delta u, delta x. Take the derivative with respect to x, you get 0, because the derivative of 0 is just 0. Same thing for w. So this term goes away, this term goes away, so now you're just left with this is equal to 0. So that's what you get here. Take the second derivative again, and it's also 0, okay? So now v over y squared, that's that one right here. This went away. So now we're left with this one, delta v over delta y. That term goes away. So now this went away, this went away, this went away, this went away. So far we still have this, and it makes sense, right? That's what we're solving for the pressure gradient. We're solving for this term right here. Gy became negative g, and then we're just down to this term. And it makes sense, right? It's telling you, hey, how does the y up and down, how does the y velocity change with respect to x, okay? So it could be like very small here, very high here, as you can kind of see. So this was just pure intuition, right? I'm kind of thinking about it, because at the plates, you're gonna have no slip. So the fluid wants to stick to the walls. At the center, it's kind of like not sticking, right? So at the center, it's the highest, and then because this is no slip, it kind of forms a parabolic shape, okay? So I was just using like intuition, kind of like understanding what the flow is gonna look like. But technically, I just drew this just so you guys could see it. You don't even need to draw this like on your problems, okay? This is just like, so I can explain going into the paper, that's what it looks like, okay? So now that we reduced the Navier Stokes equation, right, we got all the terms that cancel out. Now we can just rewrite it. So in this case, it's that term that I said, minus g plus nu delta squared v over delta x squared. Okay, now I just rearrange it. I know nu is equal to mu over density. So what I did was I multiplied density to everything. So if I multiply density to everything, this goes away. It's just negative delta p over delta y. This becomes negative rho gy, okay? This stays the same. I mean, this will become nu over, I'm sorry, hold on. Nu is equal to this, okay? But so I'm gonna replace it, mu over density. Now, if I multiply density to everything, that density goes away, so that's just mu, okay? So that was how I rearranged it right now. I just moved these two terms to this side, okay? And then this is what I did. I just did the substitution that I told you about, and I just multiplied density to everything pretty much. And then I also isolated v. Okay, I just did math at this point. I'm sorry if it's a little confusing, but you should be able to go from here to here using this relationship, okay? Just take your time with it, and you should be good. Nothing crazy. Now, step 6 is when you start, oh, I'm sorry, hold on. Before we go to step 6, now you start integrating to find your general solution, okay? So you had this delta squared velocity in the y over delta x squared, right? So you start integrating, that's it. You isolated this one, okay, from here. You moved everything over here. So that nu got converted using this and then just moved this way. I integrate it with respect to x once. So I get delta v over delta x, it's no longer squared. And I put an x plus a constant, okay? Then I integrate it one more time. Then it becomes x squared over 2, right? And this stays the same. And then c1x, it gets an x, and then you get another constant. And ignore this for now, you'll see what I'm gonna do. Now that you have two constants that you don't know, you get two boundary conditions. In this case, like this problem, you could get 3 boundary conditions. So I labeled them 1, 2, and 3. So I told you guys at the wall, it's a no slip condition. The velocity is 0. The fluid is stuck to the wall, okay? That's kind of just a general rule for fluid mechanics. You're gonna need it going into future classes, master's program, if you start taking that. That's just no slip, right? It just means that the fluid at the wall, it's stuck, that's it. And then it kind of, obviously as the fluid is flowing upwards in this case, it creates a parabolic curve, okay? And we know it creates a parabolic curve because look, this is the function. So if you graph this function on here, look, this is a parabola, x squared, and it comes downward, right? So positive x squared. And then the rest are just constants, right? But at the end of the day, that x squared tells you that it's a parabola coming down. So look, I know here velocity 0 and here velocity 0. So what I could do is boundary condition number 1, which is what I did here. At x equals 0, right? This is x equals 0. This is x is equal to h, right at the center. And then x is equal to 2h, okay? I know at x equals 0, right here, my velocity is 0, okay? So I'm able to use this relationship. Again, ignore this for now. But I'm able to use this relationship. For velocity, you plug in 0. So this is 0 equals, then for every x that you see, plug in 0. So this is 0, so this times all this is 0. And then C1 times 0 is 0. So that's what I got here. 0 is equal to 0 plus 0 plus C2. C2 is equal to 0, okay? So now look, I get the second boundary condition. You could choose either or, and they'll give you the same result. In this case, let's stick with this one, just that because we're talking about no slip, so might as well just stick to it. Let's use condition number 2. Oh, it should have been condition number 3, I'm sorry. But condition number 2, at x is equal to 2h, okay? Your velocity is 0. So this velocity, look, the reason I did this is the same as this, okay? These two are the same. All I did was factor out an x from x squared plus all this plus c1x. So x, and then look, that x just became regular x over 2 mu, the constant plus c1, right? That x got factored out. This here is the same as this, if you notice, okay? But that's the change in v over change in x. So this is telling you how does the velocity change with respect to x. And we know here that change in v over change in x is 0, right? The slope is 0. So that's what it's saying. So let's assume we're using this boundary condition, right? X is equal to 2h. So let's plug it in. For this equation, plug in, for every x that you see, plug in 2h, okay? So we know C2 0, right? We already found that. So this goes away, ignore it. Divide x to both sides. The reason, this is 0 right here, remember, right? Velocity is 0 at this location. So this is 0 divided by x, well, the x just goes away. Now you put in, for every x that you see, you put in 2h. So 2h over 2 mu will give you h over mu, right? Plus, times all this plus c1. Well, now solve for c1, so move all this to the other side, it just becomes negative. And you get negative h over mu, parentheses the constant, okay? That constant right there. Now you solve for c1. Now let's solve it using the center boundary condition. So at x equals h, the change in velocity is equal to 0. So this is 0, and then for every x that you see here, plug in h. So it's just 1h right here. H over mu times the constant parentheses plus c1. We'll solve for c1, just move this to the other side. And there's 0, remember, so move it to the other side. And yeah, you get the same answer. And I'm going to solve this, again, in the same video. I'm going to solve it using different origins, and you'll see how it's the same thing. The velocity profile just changes a little bit. But it all depends on where you set your origin. In this case, I set it from the very beginning. The problem sometimes likes to set it at the middle. So it's x equals negative h and x equals positive h. But it gives you the same result. So that's that part, right? Let me go to the part 2. Let me kind of cover the answers right here just for now. So check it out. The particular solution is just a general solution with the c's incorporated, okay? So in this case, I already have my general solution here. This is the general solution, v of x. I found c1 and I found c2. So plug them in, and that gives you my particular solution. Okay, so in this case, I got x squared over 2 mu times a constant parentheses plus c1, which is a negative h over mu, times x. So it becomes a negative x h over mu times a constant. Just factor it out, right, because they both share the same constant. So in this case, I'm going to have x squared minus 2xh, right, because I had to multiply this one by 2 in order to add them together, 2 mu at the bottom. So this became a negative 2xh times the constant. That's the parentheses, okay? So we found our particular solution, okay? Now to find the expression for the pressure gradient, in the direction of the flow in terms of mean velocity, we have to get the mean velocity first, okay? This is not the mean velocity, this is the velocity profile. To get the mean velocity, all you do is integrate this with respect to your distance, in this case, 0 to 2h, and you divide it by the total distance, which is 2h, okay? So that's what I did here, okay? Right there. The mean average velocity is just v of x integrated from 0 to 2h, and then you divide it by your total distance. In this case, is 2h, okay? Nothing crazy. So I'm gonna plug in this function here, and it's very easy to integrate. It looks complicated, but it's not, because all this is just a constant, so it could just come out. And look, that's what I did here. Okay, so 1 over 2h, that's that one, it's right here. Then I integrated it. I separated these two terms, just FYI. So I put x cubed over 6 mu, right? I did this term first, and then I'm gonna do this term next, okay? So x cubed over 6 mu, that's what you see here, times a constant, minus, integrate this, it's x squared over 4 mu, but there's already a 2. So I just simplified it, x squared over 2 mu times h times a constant, okay? Now what I did was I just combined the terms, right? These two terms, so, because they both share the same constant to multiply it to. So in this case, I did x cubed over 6 mu, which is that term right there. And then this one I had to multiply by 3 top and bottom to get the 6 mu at the bottom. So you get negative 3x squared h. And then times a constant, and then again over the times 1 over 2h, okay? So here. Simplify this, and you will get negative h squared over 3 mu, okay? Because that became a negative 2x squared. Oh, I'm sorry, hold on. Before I do that, I gotta apply the 0 to 2h, okay? And look through this, but that's kind of what I did here, okay? I plugged it in, so 2h in this case, because when you plug in 0, it's just 0, so just plug in the 2h in the first. You know how like it goes from like 2h to 0, like if I was to draw the line here. I didn't do it here, but like I draw the line down and then 0 to 2h. Well, in this case, because the second term is just 0, I'm just gonna plug in 2h and that's it, call it a day. So this becomes 8h cubed, right? When you plug it in for x, 8h cubed minus 12h cubed, okay? So when you do that, you get negative 4h cubed divided by 6 mu, you get negative 2h cubed over 3 mu. But then you multiply that 2h here, right? That 2h got multiplied times this, the negative 2h cubed. So that just became negative h squared. And it's just algebra, okay? I'm just explaining what I'm doing. And then times the constant. So now this is the average velocity. And now all I need to do is solve for this delta py, okay? Isolate it, and that's your answer. That's finding the expression for the pressure gradient and the direction of the flow in terms of mean velocity. And boom, we found it. Now that's the answer. You can stop the video right here if you want, no big deal, but I'm gonna show you that changing the origin doesn't affect your answer, okay? So I'm gonna repeat steps 6 through 8, which is step 6, boundary conditions, through 8 up until here, right? And I'm just gonna show you the whole paper at this point so you can see. But same thing, right? In this case, we already had these two, okay? I just copied and pasted them from here, okay? So let me make sure you guys could see right there, maybe right there. Oh, actually right there. But I just got these two and I threw them in here, okay? Just so you know, kind of thing. Now I'm gonna apply boundary conditions. I got x equals negative h, x equals 0, x equals h. So at x equals 0, we know velocity is 0. The change in velocity is 0, I'm sorry. So right here, down the middle, x equals 0, change in velocity is 0. So that means my C1 is 0, right? Because I'm going to use this equation because change in V over change in X. So this is 0. For any X you see, plug in a 0. So this is 0 times all this is 0. So C1 is 0. Boom. Now I could use either or, and then I could say velocity 0 at that location, okay? So in this case, I chose positive H. And when you plug in positive h for your velocity function now, because this is 0, right? So 0 times all this plus 0 times all this, that means, hold on, oh no, I'm sorry. You plug in h. Wherever you see an x, you plug in h. So this becomes h squared over 2 mu, right? Plus c, well, c1's already 0. So you get h squared over 2 mu plus all this times all this, and then you just move it to the other side and solve for c2. And that's what I did. Now, if you would have used, you could have used the other boundary condition, right? Use x equals negative h now. Plug in negative h, well, you square it, and it becomes positive anyway, so it's the same thing. This one went away because it's 0, so it doesn't affect us in any way, and you get the same answer. Now, you get the particular solution. Now, this c2, you plug it in here, and this 0, you plug it in here, right, for your general solution. Plug these c1, c2s in, and then you have your particular solution. And go ahead and do that if you want, but that's what you get. Now, if you look at, compare this, let me move this down a little bit. Compare this to this. This is where we're at. They kind of look identical, right? The term here stayed the same, right? That's that term. By 2 mu was divided, but look, x squared minus h squared here, x squared minus 2xh. And that's just simply because the origins are different. But once you get that, now you're able to find the mean velocity just like we did in step 8, right? Just follow the same steps. So I integrated it from h to negative h this time, not from 0 to 2h. So when you do that, plug in all your numbers and feel free to do it on your own, but that is the answer that you get, which is the same as the average velocity here, okay? So if that's the same, that means solving for delta p, delta y is gonna be the same. And I just realized I put x, that should have been a y, okay? But yeah, that is the answer, and that is how you do this problem for Navier Stokes. Let me make sure you guys were able to see the entire paper. That's the top, that's the bottom, and then that's the top right here, and that's the bottom. But yeah, hope that helped.